is common knowledge that life has left fossil traces of its history. Patient decrypting of these vestiges has allowed paleontologists to conjure up from the remote past the ghosts of ancient plants and animals, and to piece together a rough evolutionary history of the organisms that inhabit our planet today. However, the fossil record is very incomplete. Quite often, a single bone or tooth, the imprint of a leaf, or the hollow cast of a worm is all that is available to reconstruct an entire organism. In addition, the fossil record hardly goes back further than 600 million years. The earlier record is extremely sparse. Countless organisms must have existed that have left no trace or whose traces have not yet been unearthed. Were only fossil documents available, however numerous and well preserved, a complete history of life could not be written or even contemplated. Our information comes not so much from dead remains as from living beings. The whole history of life is written into present day organisms. All we need in order to reconstruct this history is to be able to read that text. This we can now do using the comparative sequencing of related macromolecules from different kinds of organisms. Such analysis can serve to evaluate the evolutionary distance between a pair of organisms, sisters, first cousins, 10 times removed cousins, and so on, taking as a yardstick the number of differences between the compared sequences. The more numerous these differences, so the assumption goes, subject to a considerable number of caveats and qualifications, the longer the time the molecules have been evolving separately, that is, the longer the time since the species possessing the molecules diverged from their last common ancestor. With enough information of this kind, it is possible, in principle, to reconstruct the entire tree of life on the basis of the properties of organisms living around us today. In a linguistic analogy, such an approach amounts to molecular etymology. Imagine a linguist confronted with only contemporary texts like French, Italian, Spanish, and Romanian. Even without knowledge of the past, such an expert would be able to conclude from the many similarities among words of the same meaning that these four languages are related. By careful comparative studies based on the assumption that words change only gradually with time, he might even succeed in reconstructing the ancestral Latin as well as the manner in which the four languages evolved from it. These reconstructions would be shaky at first, easily led astray by coincidental similarities, appropriations by one language from another, and other red herrings. But it would become increasingly secure as more words were examined, analyzed, and compared. One of the early examples of molecular etymology, now a classic, concerns a protein called cytochrome. This small protein, about 100 amino acids long, participates in the utilization of oxygen by many living beings. The human version of cytochrome differs from that of a rhesus monkey by a single amino acid, and from those of the dog, rattlesnake, bullfrog, tuna fish, silkworm, wheat, and yeast by 11, 14, 18, 21, 31, 43, and 45 amino acids, respectively. Such figures provide estimates of the increasingly remote times when each of the species branched from the last ancestor they have in common with us. These estimates, which fit with the fossil record for the animals, go further back in time to kinship for which no fossil evidence exists. Note that even the wheat and yeast cytochrome molecules share more than 50 amino acids with each other, and with the human molecule, indisputable proof that these three widely different species have a common ancestry. Comparative sequencing of cytochrome C was done more than 20 years ago. Since then, many proteins as well as nucleic acids have been similarly compared and more are being analyzed every day. Interpretation of the data is not simple. Nevertheless, even though many uncertainties and controversies are left to be resolved, we're beginning to know in some detail and with some degree of confidence the manner in which extant living forms originated from their common ancestor by a progressive branching of the tree of life. In its upper part, the molecular tree agrees with that drawn by paleontologists on the basis of fossil evidence, except for a number of details that have been added or corrected with the help of the new data. The lower part of the tree is new to us. It has proved surprising.